So the voltage-controlled oscillator is one of the most important components of the phase-locked loop. So let's take a moment to understand how the voltage-controlled oscillator, or VCO, is going to work. So let's assume that we have a simple linear VCO. The simple linear VCO, if you connected it to your breadboard, if you bought it as a component, you would connect it to some power, and then you could have an input and an output. And if you put no voltage into the input, it's going to run at a free running frequency or quiescent frequency. So if there's no input voltage, the instantaneous output frequency of your VCO is going to be some frequency, and we're going to call it omega C. So that's the free running frequency of your VCO. Now, if it's a simple linear VCO, that instantaneous frequency is going to vary based on the input signal that you give it. So if we gave it some input signal, and we call it E0, then it's going to vary linearly with E0 based on this constant coefficient, where this is our input signal. So this would mean that the instantaneous VCO frequency, so this is the instantaneous frequency that you get at the output of your VCO, is going to be this frequency, your free running frequency plus something that varies with the input. And then what would be the output angle at your VCO? Well, we're going to need to integrate this, and we're going to make a slightly different definition, or we're going to use theta in a slightly different way than we've used it previously. We're going to say that the output angle, right, is this time-changing carrier free running frequency. And then we're going to use theta to denote phase. So this is the output phase. So the VCO output angle is going to be that free running frequency that's varying with time, plus the output phase, which is going to vary with time. And it can vary with time because our E0 could also vary with time. Now, the instantaneous frequency at the output would be the derivative, right, of that output angle. So if we take the derivative of this, we'll denote that by a theta O dot, where we define theta O dot as being equal to that signal that we put in at the input. So this input signal is the derivative of the output phase. So the combination of this is that we have an instantaneous output frequency, and that one is the free running frequency plus the derivative of the phase, and the output angle is the free running frequency varying with time plus the output angle varying with time. So let's take a look at a block diagram to understand this better. So you have some input signal, and that's E0, E output. And that's going in to the input of your VCO. Out comes a instantaneous frequency here that is changing based on whatever that free running frequency of your VCO is. And then we could say that the output signal from that VCO is going to look like this. It's going to be an oscillating function, a sinusoid, which is oscillating. And inside, right, the angle of that is going to be the free running frequency varying with time plus this phase, this output phase, where the output phase is based on the input. So when you take this input, if you were to integrate that, right, this would give you the output phase. All right, so this is going to be how the voltage-controlled oscillator works for this basically a simple linear case that we're going to assume for our purposes.